Hello everyone. Thanks for your interest in our latest research, titled DynamicDet, a unified dynamic architecture for object detection. Dynamic neural network is an emerging research topic in deep learning. With adaptive inference, dynamic models can achieve remarkable accuracy and computational efficiency. However, it is challenging to design a powerful dynamic detector because of no suitable dynamic architecture and exiting criterion for object detection. To deal with these issues, we first design a dynamic architecture for the object detection task, with an adaptive router to choose the best route for each image. In addition, we propose a hyperparameter-free optimization strategy and a variable speed inference strategy for DynamicDet. Extensive experiments show that DynamicDet can achieve a wide range of state-of-the-art accuracy-speed trade-offs with only one dynamic detector. Now, we will proceed to share detailed information about our work. The first part is the introduction. The human brain inspires many fields of deep learning, and the dynamic neural network is a typical one. In the two examples shown in this slide, we can quickly identify all objects on the left easy image, while we need more time to achieve the same effect for the right one. In other words, the processing speeds of images are different in our brains, which depend on the difficulties of the images. Thus, extending from the human brain to the neural network, researchers proposed the early exiting mechanism. However, it is challenging to adopt current dynamic inference methods for object detectors. Starting from the model architecture of different tasks, we can see that the decoder of image classification task is very light and only relies on the single scale feature, which makes it achievable to insert the decoder at any position to realize early exiting. On the other hand, the decoder of object detection task is heavy and strongly relies on multi-scale features. This raises a challenge to implementing dynamic object detection. Next, we will introduce our approach, which consists of 4 parts: overall architecture, adaptive router, optimization strategy, and variable speed inference. The overall architecture of our dynamic detector is shown in this figure, which is evolved from CVNet and consists of 2 detectors and 1 router. During the inference, for an input image, we initially extract its multi-scale features with the first backbone. Then, the router will be fed with these multi-scale features to predict a difficulty score 5 for this image. If the router classifies the input image as an easy one, the followed neck and head will output the detection results. On the contrary, if the router classifies the input image as a hard one, the multi-scale features will need further enhancement by the second backbone and the detection results will be obtained by the second head and neck. Through the above process, the easy images will be processed by only 1 backbone, while the hard images will be processed by 2. Obviously, with such an architecture, trade-offs between speed and accuracy can be achieved. We design an adaptive router based on multi-scale features, that is, a simple yet effective decision maker for the dynamic detector. For the input multi-scale features F1, we first compress it with global average pooling and concatenate them all. Then, we map the compressed vector to the difficulty score via 2 learnable fully connected layers. Notably, sigma and delta denote the ReLU and sigmoid functions respectively. To train our dynamic detectors well, we introduce a hyperparameter-free optimization strategy here. Firstly, we jointly train the cascaded detectors, and the training objective is here. X and Y denote the input image and the ground truth respectively. Theta I denotes the learnable parameters of the detector I, and Li denotes the training loss for detector I, for example, the sum of bounding box regression loss and the classification loss. Then, we train the adaptive router to automatically distinguish the difficulty of the image. We first freeze the parameters of 2 detectors. Here, we give 2 naive methods. If we directly optimize the router without any constraints as method 1, the router will always choose the most accurate detector as it allows for a lower training loss. Furthermore, if we naively add hardware constraints to the training objective as method 2, we will have to adjust the hyperparameter lambda by trial and error, leading to huge workforce consumption. To overcome the above challenges, we propose a hyperparameter-free optimization strategy for our adaptive router. We define the difficulty criterion based on the corresponding training loss difference between 2 detectors of an image. Specifically, we assume that if the loss difference of an image between 2 detectors is small enough, this image can be classified as an easy image. Instead, if the loss difference is large enough, it should be classified as a hard image. To achieve this automatically, we introduce an adaptive offset to balance the losses of 2 detectors and optimize our router via gradient descent. We first calculate the median of the loss difference between the first and the second detector on the training set delta. Then, we use the half of delta to reward the first detector and punish the second detector, and the training objective is this equation. As the qualitative analysis shown in this figure, with this reward and penalty, the loss curves of these two detectors intersect and reveal the optimal curve. We further propose a simple and effective method to determine the difficulty score thresholds to achieve variable speed inference with only one dynamic detector. Assuming the latency of the first detector is lat1, the latency of the cascaded two detectors is lat2, and the target latency is lat-t, the difficulty scores of the validation set is s-val. We first calculate the maximum allowable proportion of the hard images k. Then the threshold tau-val can be calculated by the percentile function. Then we can directly use this tau-val on the test set because these two sets are independent and identically distributed. Next, we will show our extensive experiments conducted on the COCO benchmark here. As shown in this table, our dynamic detectors obtain better results and achieve new state-of-the-art accuracy-speed trade-offs. Specifically, DynamicDet 7W690 achieves 56.7% AP with 48 FPS, which is 0.1% more accurate and 17% faster than DynamicDet 7D6. DynamicDet 7W6100 achieves 56.8% AP with 46 FPS, which is 39% faster than DynamicDet 7E6E with similar accuracy. It is worth noting that these trade-offs are obtained by only one dynamic detector instead of multiple independent models. And this is the accuracy and speed frontier figure for the above table. We also conduct experiments on two classic two-stage detectors, faster RCNN with ResNet and mask RCNN with SWIN transformer, to show the generality of our dynamic det. As shown in the table and the figure, our method is compatible with these detectors and can also improve the accuracy-speed performance of baselines. Then, we depict the images with different predicted difficulty scores, ascending from left to right. We can observe that the easy images usually contain fewer objects, with the usual camera viewpoint and a clean background. In contrast, the hard images usually have more complex scenes with severe occlusion and much more small objects. Last, about the conclusion. In this paper, we present DynamicDet, with a dynamic architecture, an adaptive router, a hyperparameter-free optimization strategy, and a variable speed inference strategy. Extensive experimental results demonstrate the superiority of DynamicDet in accuracy and efficiency, and a wide range of state-of-the-art accuracy-speed trade-offs is achieved. Thanks for your time and attention. If you have any questions, please feel free to reach out to me at any time.